Welcome to Turbine Engine Hygiene, sponsored by RotorDoc LLC and Helicopter Maintenance Magazine. I'm Mike Broderick, and I own RotorDoc LLC. I represent Helicopter Maintenance Magazine. You will see my information down below. Should you have questions, go ahead and take this down, write the questions down, and then you can email me, and I will repeat this stuff again at the end of the presentation. Below, you will see also an FAA approval for this presentation individually. That way, should you only get an hour's worth, at least you can copy this number down, and they will give you credit for an hour based upon this number. Okay, let's get on with it. So today, we're going to talk about everything you always wanted to know about water, but were afraid to ask, and as of course, it's explained by me. Now let's get on with the admin weenie stuff here from Dewey, Cheatham, and Howe. This is the legal advisory. The information in this lecture is based upon the collaborative assemblage of instructions published in the operations and maintenance manuals from engine and airframe manufacturers, as well as the experience of the presenter. That's me. The recommendations offered here are not intended to replace the instructions in those accepted publications, but rather to assist the technician in their day-to-day maintenance activities. That's you. Lastly, the cocktail knowledge, or CK, as you'll find out, also shared by the presenter, again, that's me, as well as the shameless effort at humor are interposed with the boring facts of this discussion to keep the dry subject about water interesting. All right, everybody got that? Then let's move along. So cocktail knowledge, for those of you who have not sat in any of my presentations before, let me give you a quick definition. It's knowledge and use of little known or arcane information that when repeated during social functions leaves a positive impression of the raconteur. That would be you. So all of this information you can share, and you'd be surprised how you will impress the impressionable, depending upon where you are. So the topics today for hygiene for topics for today, we're going to have a definition of turbine engine hygiene. We're going to talk everything you always wanted to know about water. We're going to talk about the chemistry and categories of water, methods of purification, chemistry and agents of corrosion, air and airborne contaminants and erosion, brief review of turbine engine operation, and then the benefits of proper turbine engine hygiene. So I equate turbine engine hygiene much to like brushing your teeth. And I'm sure if I was to ask for a show of hands, everybody would say that they all brush your teeth. And when do you do it? You do it at night. That's the last activity that you do before you go to bed. And you do it so what? So that you can keep those teeth rather than have them replaced by some choppers that are showing there. Well, we brush our engine's teeth to prevent compressor corrosion. And here is a nice shot of a compressor that has been experienced corrosion and other ultimate failure. This is a Rolls-Royce 250 C20B compressor. It suffered third stage blade failure. I'm familiar with this action as it's happened. I've inspected quite a few of these. And I can tell that it was a blade failure after the first stage. There's no damage to the inlet side of the first stage compressor wheels. So what happens is a blade becomes thin either through corrosion and erosion. As it moves through the air, compressing the air, it will break off, move aft, move forward, move aft, and move back and forth, destroying the blades as it goes. Eventually, it will stop the compressor and with such force that they will draw the air from the compressor combustion section and burn the compressor as it's seen here. So what is turbine engine hygiene? It is an engine cleaning function that using dihydrogen monoxide as the medium that when routinely performed is conducive to prevention of corrosion, preservation of engine performance, and reduction of operating costs. And we'll go through each one of those things as we progress. OEM recommended solution for turbine engine hygiene is dihydrogen monoxide. And Cocktail knowledge alert, that's our first one. What is dihydrogen monoxide? It's water. The chemistry of water is such, looks like a little Mickey Mouse face here with the hydrogen ears on either side, the positive side of the molecule, and oxygen with the smile or negative oxygen. They are attracted to one another. This forms H2O, or water. These droplets all get together. They have a north and a south pole, which would be the positive side would be north and the negative side would be negative. The south pole would be the negative side. Good going, Mike. They are attracted to one another. And as they attract to one another, they form drips or drops like you see here. And the drops all get together and form a big collection of water, as you see here. So water is a multi-purpose liquid. And by that, I mean water is colorless, odorless, and tasteless. It's essential for the sustenance of life. It's an additive to food and beverages. It's a coolant for engines and machinery. It's a household and cleaners. It's used as a fire retardant. And it's the universal dissolvent. All of these I'm sure you're aware of, but I'm sure you don't understand what the universal dissolvent might mean. Well, let's take a look at the word dissolvent. Dissolvent from the Latin dissolve, dissolvens, defined by Funk and Wagnall's New World Dictionary, a liquid that can dissolve other substances. A dissolvent substance, a solvent. So, as a universal dissolvent, water will absorb certain non-organic chemicals. This is the combination of salt, sodium, and chloride. Now look what happens when they are attracted to one another. The positive side of the sodium goes over to the negative side of the oxygen, and the positive side of the hydrogen connects the chloride. Let me show you in a demonstration here. Pour some water in a glass, pour a little salt into the glass and stir it up. And what we have is, you can see the salt is dissolved and becomes part of the solution for the water. Now, every solution is unique in its reaction to stimuli. Let me show you what happens when we pour water in a glass and stimulate the edges of it. You'll get a unique sound out of the water. Okay, now we have a solution of water, and we pour it into a glass and do the same test, and we'll get a different reaction to wetting the sides of the glass. Part of my vain attempt at humor. So, is water attracted to organic stuff? No, it is not. What it will do is it will move it around and push it in different and change its shape, but it will not absorb it like it does with salt or inorganic materials. So organic stuff is not water soluble. And just to demonstrate, here is a mound of clay and water flowing over it. You can see that it's changing its shape. It's pushing it around, but it is not absorbing it. When we get done with this experiment here, you'll see that there's just nothing but a pile of the clay, same amount that was there before the water flowed over it. So therefore, oil is organic and also not water soluble. That's why it floats on top of the water. It will not be absorbed by the water. Therefore, oil is not dissolved by water. Here's what happens. You put a water droplet in with the water, and it is not attracted to, they are not attracted to each other. So water is essential in cleaning. We've determined that. So how do we get rid of the grease and the oil if the oil and the grease are not affected by water? So water needs help when it comes to removing grease and oil. And how do we do that? We remove grease and oil we use a detergent, soap or SO4, sulfur tetroxide. It's the negative tetroxide of the SO4 is attracted to the positive side of the water. The sulfur leg of the SO4 attaches itself to the oil, and together the oil, the SO4, and the H2O flow down the drain. So this is what happens during the chemical reaction of soap and water against oil. And as you heat up water, just as an added bit of information, that's why your mom always told you to heat the water up. It will remove the oil at a faster rate. So that's why you heat the water when you go to wash your hands. All right. So the water, the soap, and the oil all end up going down the drain together. So let's go through the categories of water. There's raw water, which has not been boiled. Hard water, this is saturated with calcium, iron, magnesium, and many other inorganic materials. Boiled water, boiling helps remove some of the germs, but it concentrates the inorganic minerals and deposits them on the side of the container. Rainwater or snow. Now this has been condensed from the clouds. The first drop is distilled water, but when it falls as rain, it can pick up the germs, dust, smoke, minerals. Strontium-90, a little bit of more cocktail information. Strontium-90 is what's left in the atmosphere after 70 years ago of atom bomb testing in the atmosphere. It's amazing that stuff is still around. Lead and many other atmospheric chemicals. By the time the rainwater reaches the earth, it can be so saturated with dust and pollution that it may even be yellowish in color. So water in this category is acting like an atmospheric purifier, much in the same way as that acts when it's used upon your engines to remove the contaminants. Filtered water, of course, passed through a fine strainer or called a filter. Soft water. The water is soft in comparison with hard because it has had the minerals removed. Much like the hard water has still got the calcium and stuff in it, we remove that. That's how you get soft water. Reverse osmosis. This is a system of water purification which allows the water to be forced through a semi-permeable membrane to separate the impurities. And of course, deionized water. This is water that has had almost all of the mineral ions removed via an ion exchange process. AKA, that's how you get soft water. And of course, distilled water, which is the purest form of water. This is water that has first been heated into steam, separating the H2O molecules from the contaminants. During this vapor phase change process, the water volume increases by a factor of 1600 so that all the contaminants are released and left behind. Then through condensation, the steam returns to liquid, waterless all of the impurities. It has been purified. Distilled water becomes ultra pure and only truly pure water with a final process of deionization known as polishing. This is water that is free from all contamination, enhanced, ultra pure, and distilled. Of course, now we've got polluted water. Little cocktail knowledge here. The Great Pacific Garbage Patch contains 79,000 tons of discarded plastic. This is plastic that has made it to the ocean and is now tried to get over to Hawaii. Covering an area of about 617,800 square miles. It's twice the size of the state of Texas. It lies partway between the Hawaiian Islands and the U.S. left coast, and it's because of the circular currents in the ocean. It is kind of corralled up into one big patch. Here's what it looks like with a diver in the middle of it. It's all the plastic bottles and sacks and bags that have been picked up off of the beach and floated into the water. So we know water attracts inorganic stuff. This is the inorganic stuff that it will attract: ash, calcium, magnesium, chloride, sodium, sulfate. How do we get the inorganic stuff out and get the pure water in for cleaning? Well, we use filtration, reverse osmosis, which we partly described, deionization, and of course, distillation. Filtration. This is typical filtration methods, or it's a barrier. What it does is the contaminated water enters one side, the contaminants are held by the filter, and the filtered water goes through the other side. Typical barriers include carbon filters, reverse osmosis, ceramic filters, and sediment filters. So what reverse osmosis, exactly what is it? It is a form of filtration. Water wants equilibrium and of concentrates suspended within it. Osmosis occurs naturally. Water of a low dissolved concentrate will move through a filter to mix with the water of a high dissolved concentrate, on the other side seeking equilibrium. Reverse osmosis occurs when the pressure is applied to the water of the high dissolved concentrate, forcing it in reverse through the filter to join the water of the low dissolved concentrate. This is how they use seawater out on the cruise ships in order for you to get fresh water for your showers and your ice for your drinks. They pressurize the salt water, forcing it through a filter, depositing the salt on the one side of the filter, and combining with the fresh water and sending it out throughout the air, throughout the ship. Cocktail knowledge alert. Your sweat glands use osmosis. Your body doesn't pump water to your skin. It deposits a little bit of salt inside each of your sweat glands. And since your body is 70% water, it's attracted to this salt. Great stuff you guys are learning here. You can use this and impress many people. So let's talk about the deionization process. Currently, two of the primary applications of ion exchange are water softening and deionization. The softening process used in industry and popular in homes uses an exchange resin to remove the calcium and magnesium ions from the water. You can see the magnesium ions are indicated here by the red, blue, and green signs. And the water containing these minerals comes through the one side. The ion exchange material, which is hydrogen, which are called cations, and hydroxide, which are called anions. The ion exchange resins are solid polymer materials that hold fixed positive and negative charges. These charges are exchanged with the mobile cations, and the positive, which is the positive ion, and the anions, which is the negative ion, and which produces an ion exchange. Okay, let me get out of this, whatever that is. And of course, we have distillation. Distillation occurs naturally in the world. The water is evaporated by the sun, condensed into clouds, and then the clouds form and drop the water in form of precipitation. And that's the purest form of water right there. Aviation distillation system. It's the same thing as what happens in nature. You get the water, goes through the evaporation process where it is condensed and drops off all of the inorganic chemicals that are held or suspended within the water. The now condensed steam turns into water and precipitates into the tank, the holding tank, and you have pure H2O to be used for, well, they can show you can even use it for coffee, or you can use it for cleaning your turbine engine. The OEM recommended solution for turbine engine hygiene then is ultra pure distilled water. That's a picture, of course, of the Rolls-Royce 250 C30 engine. So distillation is the most consistent method of purifying water and for use for aviation purposes. Reverse osmosis and the carbon filter, of course, drop off as the filters become overburdened with the debris that they're picking up and have to be changed over each period of time. So the most consistent, of course, is distillation. This is the Turbomeca distillation water specification. The U.S. Coast Guard also went to a company that created a system, a aviation-specific distillation system, based upon what the Coast Guard was requesting, and that was based upon Turbomeca's specification. Coast Guard was tired of paying for all of the corrosion, of course, since they are exposed to a lot of salt water. They were tired of paying for the corroded damage to their engines, and so they needed somebody that would create a water distillation system for them to use. Now, the maximum, let me give you some explanation of some of the terminology here. The maximum US that's units suspended per centimeter. That's what that does is that's the maximum amount of impurity that remains in the water, and that's an electrical conductivity check. The greater this number, the more the water becomes able to pass electric current, and it's also more contaminated. And as you can see, it was all acceptable. The person over here that made these systems got it down to 2 USPCMs. The pH, now that's the alkaline and acidity number. 0 to 14 is the limit. 7 is a neutral indication. If you get the lower numbers, it's more acidic. As you get to the higher numbers of 14, it becomes more alkaline. So 7 is the number that you're looking for. And the ash, of course, maximum of 2 parts per million. And none of these were applicable over here because they didn't have any. And of course, this is what this is a French term for hardening of water or hard water. And they would have accepted it with the Coast Guard. However, got over here and it wasn't even part of the equation. So why perform turbine engine hygiene? Because the OEM says the engine cleanliness is conducive to prevention of corrosion, preservation of engine performance, and reduction of engine operating costs. And we'll get to those here just in a few minutes. So let's talk about corrosion. It's the silent consumer. You see the results of corrosion, but you don't see it actually happening. As you can see, it has left its mark here on this turbine engine support with the pitting, and this was all caused by contaminated water or moisture that has been allowed to lay on here without being removed. So the chemistry of corrosion. Corrosion is the deterioration of a material due to direct chemical attack. The salts hold the moisture on the surface and promote corrosion in unprotected metals. Chloride solutions break down the protective film on magnesium and aluminum. Corrosion increases with humidity. Inlets and compressor sections, protective coatings, can be chipped and eroded away by erosion, promoting the opportunity for corrosion of the base material. So corrosion and erosion, as you will see, work hand in hand to destroy the engines. And of course, then we have sulfidation, which you've all heard the term, but it's a hot corrosion process that affects the hot sections of the engine, primarily in the turbine blades. Sodium from the atmosphere, seawater, and sulfur from the fuels are sufficient to cause blistering and scaling of the turbine blades and vanes. Agents of corrosion. Airborne contaminants, these are what is floating around in the air, are particulate pollutants, gaseous pollutants, sulfur dioxide, nitrogen oxide, acid rain, smog, wildfire ash, volcanic activity, sand. All of this stuff is floating around, and it's ready to attack and corrode our helicopter as it's trying to do its job. So how do we stop corrosion? And these are the pollutants as they are floating around in the air, and these are the things that they affect. And not only are they just floating around in the air, we also produce them on the ground. So how do we stop corrosion? Well, we can do that in a couple of ways. One is we can wrap the helicopter up in a condom, makes it safe for corrosion, but it's not very practical when it comes to flying. So that's kind of out of the picture. So the agents of corrosion can be stopped with water. And that's how we mitigate against corrosion as it attacks the helicopter. U.S. airborne contaminant ratio. Now, you guys that are sitting in the Midwest thinking that you're probably in the purest air that the U.S. has to manage, it's not quite as pure as you might think. The center states, Iowa, Missouri, Kansas, Nebraska, all have mild categories of corrosion contamination. Then it becomes moderate in as you move west, and of course heavy and severe as you move towards the coast. Same thing with the east. The green is heavy, and the severe is along the coast. It's amazing to me that the Cape Kennedy region of Florida, which is where we launch a lot of our rockets, has the highest rate of corrosion in the U.S. So salt, air, acid rain, sulfur dioxide, nitrogen oxide, smog, all of these things are floating around in the air, ready to attack. Now the air, which contains all of these nice pollutants, and there they are, held by the air, they're ready to attack and eat. So the engine forces the air to work to create power. Air is basically lazy. It floats around all day, doesn't do much of anything until it is intrigued by a turbine engine and is drawn in to do work. First it's compressed, and then it's burned, and then is exercised to produce power. Air does not work for free. The contaminants within the air are corrosive, and the movement of the air through the engine is erosive. So let's take a look at the quick foray here into the 4 cycles of the engine operation. You know, the intake, the compression, the combustion, and of course the exhaust. There are 2 systems: the Brayton or the open cycle, which is what a turbine engine is, and it draws the air in. And if you'll notice that the compressor becomes smaller as the air progresses through it. This is to cause the air to be compressed. In other words, to move a greater amount of molecules, air molecules, into a smaller area. Once the air is compressed, it moves over where it is introduced to a 3,000 degree flame and gains an energy there for combustion. It now moves and has to expend its energy on turning turbine wheels in the turbine. So it is, as it expends its energy, it needs a bigger and bigger area upon which to push and thus the larger size of the turbine wheels are at the exit of the turbine. You get work out, and then of course the air, after it's done all of this stuff, is exhausted and leaves through the exhaust system. Next, you have the Otto cycle, which is what you're all familiar with. That's what you drove to work today. Piston, of course, moving up and down, valves opening and closing, allowing fuel and air mixture ratio and exhausting out. We're going to go through, this is a cutaway, which is kind of a neat cutaway. It actually rotates and shows you how things work inside of a Rolls-Royce, again, 250 C20B engine. But first, I want to talk about two terms that are interchanged with one another, which are actually is kind of incorrect: compressor surge and compressor stall. Let's discuss the theory of lift real quick so that you understand what I'm talking about. We're going to use Dan Bernelli's equation, which is the difference in pressure produces lift. Longer path equal transit. In other words, you have an airfoil and the air moves, it is greeted by the nose of the airfoil. It splits. Part of it goes underneath the airfoil, part of it goes over the top. The part that goes over the top increases in velocity so that it can catch up with the lower velocity air that goes underneath. Low velocity creates a high pressure. High velocity creates a low pressure. Air flows from a high to a low, and therefore you get lift. That's the simple process of lift. That's the way it works on wings. That's the way it works on airfoils within the compressor. So let's talk about compressor surge and compressor and the blade stall. Here you see the airflow over the airfoil, and it is adhering and doing the job that it's supposed to do. There is no blade stall. There would be no compressor surge at this particular point. Now, based upon design conditions at the left, with an increase in inlet angle at the right, the latter causing a blade stall. In other words, you either change the angle of air to the nose of the airfoil, or you change the shape of it. If you change the shape of the blade through corrosion or erosion, you're going to change its ability to process the air properly, and you're going to get a blade stall. Now, one blade does create a stall. You get a series of blades, and you get compressor surge. So compressor surge is a group of vanes or a group of blades that are stalling, and blade stall is the individual blade itself. So we have the ambient air full of all of the contaminants beating up on this compressor. And then we have air movement, which is erosive action, also beating up on this compressor, removing material as it flows through. What you get is the corrosive materials deposited on the compressor blades and by the air movement through, and you also get material removed from the blades as the air goes through. Real quick of the airflow going through the engine. Air pressure as it moves through the engine, of course, increases till it gets to the exit, the entrance of the diffuser. There it levels out and then drops off. Air pressure has to drop off or it would never flow from the compressor to the turbine, from a high to a low. That's the theory. All right. Velocity drops off, creating a higher pressure until you get to the inlet of the diffuser. There it slows down until it reaches the tip of the flame at the combustion section and speeds up. It speeds up to the point where it enters the turbine section and is angled such that it produces a good flow across the turbine blades and produces work pushing the turbine blades on the first stage turbine wheels. And then again, going through a turbine nozzle that directs the air properly through to the second stage. And then the same thing happens there. And then the air velocity drops off going through. And of course, temperature increases going into the compressor. Now, everybody calls the compressor the cold section. But if you look, you'll see it's somewhere around 500 to 600 degrees Fahrenheit at the entrance of the diffuser. That's hot enough to cook cookies. So it's plenty warm. And now, why does it warm up? Because the air molecules, as they're being compressed, putting into a smaller and smaller chamber, they begin to strike each other more often. And this collision causes the temperatures of the air to go up. Again, hits the tip of the flame, which is the tip of the flame is normally around 3,000 degrees. And then as it expends energy, the temperature goes down. And all of the air, of course, is now exhausted and leaves. So let's fire up this turbine, and I'll explain some stuff as it's going along. It all should sound familiar as the turbine is about to light off. All right. Now you see the airflow from the compressor as it's going through. It's a 7-to-1 compression ratio. It's deposited here from the diffuser down the transfer tube. With the turbine section, where it is greeted by the fuel and the 3,000 degree flame. The air now being super energized is doing work pitching on the N1 section, which is driving the compressor, and then the free air that's remaining from there turns the N2 section, which drives the gearbox. RPMs at 100%, you'll get about a 50,000 RPM for the compressor and N1 turbine, 33,000 RPM for the N2 section driving the gearbox, and you get a 6,016 output shaft speed. That 6,016 output shaft speed is about standard for throughout the industry for all turboprop engines. Now, something interesting to note, and you all wonder why we do a 2-minute cool down or 3-minute cool down on the Rolls-Royce engine. It's because of the labyrinth seal arrangement between the N1 and the N2 section, keeping the oil within the bearings surfaces. When the engine shuts off, you notice the first thing that goes away would be the air pressure that controls the pressure on the labyrinth seal. The labyrinth seal now cannot, since it has no air pressure, does not keep the oil from migrating past its position on the 6 and 7 bearing cavity. Now the oil will lay on this warm seal, labyrinth seal, and because of the temperature of the labyrinth seal, it can cook and become coke. The rotating part of the labyrinth seal will then grow enough coke to where it can attach itself to the stationary section, and you will get what they call conveniently N2 lockup. What you do during a cool down is that you normalize the temperature of that section there, and run the temperature down to the point where the skin temperature now becomes lower than what it will do to turn the liquid oil into carbon, and you don't get into lockup. Thus the 2 to 3 minute cool down on the Rolls-Royce engines. So air in motion smooths the way for erosion and removing all of the coating that protects the base material. And it keeps the contaminant, and it allows for these contaminants to attack this base material and create corrosion. So Erosion and corrosion work in concert to create compressor corrosion. So let's talk about what happens in the turbine. Turbine corrosion, also known as sulfidation. This is severe sulfidation, and I'll give you some more information on that. Same thing here. So what is sulfidation? All hydrocarbon petroleum-based fuels contain trace amounts of sulfur after refining. Sulfur, also a byproduct of combustion, is mixed with the incoming airborne salts and deposited on the surface of the gas path components. Then, aided by the velocity and temperature of the airflow, this corrosive and erosive airborne cocktail attacks the protective oxide coating on the turbine components, eventually exposing the base metal and producing a corrosive reaction. This corrosive reaction occurs at high temperature environments and is categorized by type. Type 1 is between 825 to 950. This is when a lot of the accidental hot starts are taking place, and this is the temperature range in which you're in. That's why you see the extreme burning and displacement of metal upon the turbine wheels during a hot start. And then the other would be between 700 to 800 degrees C. Now, these are the temperatures at which you're normally flying. At the high end, of course, of the 700s is you're getting into some over temps. But this is type 1, and this is the result of a type 1 over temp. And then, of course, type 2 between 700 and 800. And you see the condition of the blades, although they've been used, but at least they're going to make it to TBO. Now, something, again, a little bit of more information on what goes on during a hot start. A hot start is producing more fuel, and the flame is looking for air to support itself, and it will draw air from wherever it can. If it can't catch it in the combustion section, it will move down past the first stage turbine wheel and perhaps even find it near the second stage turbine wheel and burn that wheel, and which would leave the first stage kind of unmolested, making you think that you didn't have any damage to your turbine on a hot start. But basically, it's downstream because of, again, the air is, the fuel is looking for air and finds it downstream. So air and its gang of toxins give the gifts that keep on giving. You get corrosion, and erosion. So all engine manufacturers agree the single most proactive task for the prevention of corrosion is to remove the salts and sulfides deposited along the airframe. All engine and airframe manufacturers recommend frequent rinses and washes with pure water. Daily rinses for all engines is recommended. Daily rinses are essential for engines operated within 25 miles of salt water. If you live near either one of those coasts, you should be rinsing after the last flight of every day. All rinse and wash operations should take place after the last flight of the day. So what's the difference between an engine rinse and an engine wash? Well, let's take a look at them. For corrosion prevention, that's when you do an engine rinse. For corrosion prevention and perhaps for power recovery, pilot comes back, says, hey, the thing is running a little warmer than it did when we first took off. How about we do a compressor wash just to see if we've got some contaminants on the blades that are taken away from the efficiency of the compressor and turbine. You use soap. Daily after the last flight of the day, of course, for rinse, when required or at the 100-hour inspection is usually when you do an engine wash. Distilled water only, of course, using only OEM approved detergent and distilled water. You follow the instructions in the maintenance manual, both those. Complete a drying run. and you are finished. With the engine wash, you perform a rinse operation. In other words, once you get the soap on there and you think you've removed all of the contaminants, then you need to wash that soap off. Leaving the soap on there can be just as bad as if you hadn't done a compressor wash at all. That stuff can be corrosive on its own, so you want to rinse it all the way off and then complete a drying run and perform a power check. That's the cheapest way to determine if you've got just a dirty compressor or if you have something else going on within the engine, is after doing a compressor wash. And you have a happy running helicopter if you do that. So municipal water, that should be okay. We drink it. It should be okay, right? Nope. Contaminants in municipal water, the chlorides, the metal salts, and the sulfates are corrosive. Distilled water versus municipal water and magnesium. Distilled water versus municipal water. Using distilled water at room temperature, magnesium alloys rapidly form a protective film that prevents further corrosion. Small amounts of dissolved salts in municipal water, particularly chlorides or heavy metal salts, will break down the protective film locally, which usually results in pitting. The corrosion of magnesium alloys by fresh municipal water increases substantially with temperature. I'm going to give you an example of that here real quick. Salt solutions. Severe corrosion may occur in neutral solutions of salts of heavy metals, such as copper, iron, and nickel. Such corrosion occurs when the heavy metal basic salts, or both, plate out to form active cathodes on the anodic magnesium surface. So, preventative maintenance. This was a scrapped transmission case from a Bell helicopter, $100,000 mistake. Scrapped a good part, did not check the manual for proper processes and materials when cleaning, used chlorinated solvent along with tap water on a magnesium gear case. The technician then went to lunch, and so did the corrosion, and dined on the transmission case, and that's the result. Corrosion impact of water quality again on the turbine. Now, these blades came from a Turbomeca engine, and they came from Turbomeca themselves. The engine was flying over in Hawaii. The turbine blades were removed after 3,000 hours, and every day they did a compressor or an engine rinse using tap water. This is the result of the blades after that. Inadequate equipment and bad procedures. Same operator using pure water, the blades after 3,800 hours. So he got 800 more hours, and look at the condition of the blades. The correct equipment and procedures were used. Of course, Turbomeca is now Safran helicopter engines. So as pure water is part of the maintenance solution for good oral hygiene, you need good pure water there, and that's a nice smile. Ultra pure enhanced distilled water is a major part of the maintenance solution to good turbine engine hygiene, as proven by these blades. So why do we perform turbine engine hygiene? Because the OEM says engine cleanliness is conducive to prevention of corrosion, preservation of engine performance, reduction of operating costs. Now, the effects of cleaning an engine on engine performance. This is the line with quarterly cleanings. The engine, of course, degrades over a period of time, but it is able to at least maintain its planned degradation over the period of time and should make it to TBO. Each time that you clean the engine, you're able to bring it back up to at least your performance line. Don't do your cleaning and the engine will degrade even quicker, and you'll be removing it sooner in order for it to get overhauled. Effective cleaning will maintain available power levels at or above OEM specifications. This can be verified by daily engine power checks. Reduces maintenance costs by increasing on-wing time. If it's flying, you're not working on it, and it's making money. Fuel savings of up to 1.5% have been demonstrated by airlines performing regular rinses and washes. Southwest does this on their aircraft after the last flight of the day at the airport outside. You'll see them out there rinsing their engines, and they've managed to save 1.5% on their fuel bill. That's a tremendous amount of money when you think about the amount of money that they spend on fuel each month. And of course, increased fuel efficiencies reduce the carbon footprint. So we're nice to the environment at the same time. And we get a happier running helicopter. Now, all of the engine manufacturers, this is right out of the GE book, maintenance manual. These are all of the specifications that it talks about that they recommend that you use for keeping their engines clean. Turbomeca, the Ariel 1E2, right out of their maintenance manual. Distilled water only, distilled water and detergent. But you can see it's all right out of their manual. This is for the Ariel 2B1, same thing. Right out of the manual, tells you what kind of water you should be using. Pratt & Whitney, there you go. So all of them all agree. They all say the same thing. The type of water that they want you to use, it's not tap water. It's not water that we drink. It is water that's purified and has the contaminants removed so that it will remove the contaminants itself as it flows through the engine. And of course, Rolls-Royce, water distilled. So what is the difference between water from aviation-specific distillation system and commercially distilled bottled water? I get that question all the time. I can go down to the local drugstore or the local market and buy a bottle of distilled water and use that, leave it sitting around in the 5-gallon bottles, and it should be fine, right? Not necessarily. Let me give you a comparison here. Let's compare enhanced water from a distillation system and bottled water. For corrosion prevention, both of them do the same thing. For corrosion prevention, produced on-site and on demand. That's the difference right there. It's produced on-site and it's on demand and it's fresh when it's produced. Purchased and stored in a plastic container. And it's had the opportunity. You don't know the condition, the cleanliness of the container that holds the water when the water was first poured in there. And then the water sitting against the plastic for who knows how long could also be picking up some contaminants. So you don't know that you're really getting total distilled water. The quality of the water will be compromised over time. Follows the OEM instructions. This stuff stays the same each time you use it from your distillation system. Water quality is controlled, more economical. Storage and disposal costs of the containers you've got to worry about, and usually it's not as cost effective as you might think. Besides the obvious reasons for using distilled water, what is the side benefit gained in the process? Well, the final product is now enhanced ultra-pure water, right? This enhanced ultra-pure water is receptive to attracting and holding the contaminants it finds on the engine components as it flows through the engine. So you've got ultra-pure water, and it's magnetic, and it's looking for inorganic contaminants. And as it's looking for them, it lifts them off of the engine components by the flow activity, and then it holds on to them because it's attracted to them. So it holds on to them and makes them part of the solution that is being flushed out the back end of the engine. So enhanced ultra-pure distilled water does double duty as it flows through the engine, keeping the thing clean. And the end is near, so we're getting close here. Let's do a quick review. What is turbine engine hygiene? It's a maintenance function that through engine cleanliness is conducive to prevention of corrosion and erosion, preservation of engine performance, reduction of operating costs. Corrosion and erosion are removed or mitigated with using water. Enhanced pure water. The airborne contaminants, which we've gone through, are of course controlled through the use of water. The summary of cost savings: effective cleaning will maintain available power levels at or above OEM specs. You can find that out with a power check. Reduces maintenance costs, as we've talked about. Fuel savings, we've talked about. Increased fuel efficiencies reduces the carbon footprint. All of these savings are savings and their money back into the pocket of the operator. When do we perform our engine hygiene maintenance? After the last flight of the day. After the completion of the final flight of the day for the aircraft's flight schedule. This is usually the last maintenance activity for the shift. I know you got to wait until the engine cools down. And of course, your beer low-level warning light is flashing on while you're waiting for this to happen. But believe me, this will create a better atmosphere in the hangar when the helicopter is out flying instead of being in there with you working on it. Some of the operators that are using purpose-built distillation systems, and there's more been added since this list has been compiled. But these are some of the guys whose names you might recognize as we're going through all of this. So we are at the end of the program. I know I usually ask for questions, but I'll give you the opportunity to send me questions. One thing I want you to remember: rinse, fly, smile, and repeat. And I want to thank Concord Battery for, again, inviting me and allowing me to participate in their production of the IA seminar. This is a great thing that they're doing, and I appreciate to be part of it. Here's my contact information again. Email is rotordoc1223@icloud.com. Cell phone, give me a call. I get lonely, so give me a call, 661-644-5370. And again, the companies that the company I represent is Helicopter Maintenance, for whom I write a couple of articles, and also through my own company, RotorDoc LLC.